Y'all, how y'all doing? Here today talking about a little bit of quantum mechanics. I'll talk about a little bit of the basics and I'll see who shows, see if anybody has any questions about anything. As always, let me know if there's any issues with volume or anything. As far as I can tell, everything seems to be all right. Looks like it's going live at the moment. So on my end, everything seems good. Let me know if it's not on your end. And I'll go ahead and get started. I noticed there's a few things going on at the moment. So let's see who shows up. Hopefully everybody's more interested in some science and some dirt. I'm definitely less interested in talking about and discussing dirt than I used to be. The science and reality is so much more interesting in many respects. But it's still fun at times. So quantum mechanics. And by the way, I am in Discord. So be sure to join if you haven't. The Discord, and if you want to jump in the Discord live, you can. And I even be willing to entertain some challenges if any dirt person wants to come in. But ideally, for people who want to text about quantum mechanics and talk about it, and of course, everybody's welcome to stay in the chat as well on YouTube, and I'll be looking at that and responding as well, uh, as always. So, I guess the main thing I want to talk about is the Schrodinger equation. So, I'm sure people have heard about Schrodinger's cat, the Schrodinger guy. So basically, Schrodinger, my understanding is the one who found the equation that governs subatomic particles. So it's this equation, and there's many versions of it, but I'll talk about the time independent one today. And welcome to see somebody who showed up. My name is Daryl Lee Berry Jr. Be sure to like and subscribe if you haven't already, and drop a line in the chat to let me know you're there, or at least to interact while you're there. So basically, this is the equation, the time-independent version. So what we have here, we have this first part that's called the Hamiltonian, and this part of the equation is basically an operator that gives you the energy. So when this first part is multiplied by a state, and technically I need to do a little bit more factorization. Let me move a few things out. Right. So technically this is the Hamiltonian here. And what that basically is an operator that when you multiply this operator with a state, the state of a particle, let's say an electron, it gives you the energy of that electron. And the benefit of this is we can get the energy states of these particles, and we can construct and therefore predict future states of the particle. So basically, we get the energy state of the particle and use that to tell us things about the particle that we would otherwise. There's other ways to find out, but basically, this method is one of the most easy and straightforward methods. I guess you could say more direct methods of doing so. And this equation has a few parts. So this first part here basically refers to the kinetic energy. And this part here is basically the potential energy. And and I don't think I'm making a typo. I may because I'm not looking at notes. I'm just going off what I recall. But if I make a typo, be sure to let me know. But consider it like a general overview. I may miss a detail here or there, but a general overview of the way it works. You can think about it that way to give you a rough idea of how things work. So basically, this is the kinetic energy, this is the potential energy. And we know that the total energy of a system classically is going to be the kinetic energy plus the potential energy. So basically, this operator here takes the state of the particle and extracts out the total energy by getting us the kinetic energy and potential energy. Now, usually the potential energy is given to us. Like if you have a particle, it's going to usually be, I guess I say commonly, at least in the rudimentary phases of it, the particles is trapped in some kind of potential. So let's say we would have a potential energy, and let's say the potential energy takes this form. So this would be V of X, and the particles, because basically when we get into quantum mechanics, we're looking at the wave-like nature of particles. So in the classical sense, we have an electron and is encircling a proton. That's like the classical way of looking at it, like an orbit. But we know now that an electron, at least from the quantum wave-like perspective, technically is not really a particle, is not really a wave. Technically, it's something that I guess technically we haven't quite really defined, except that sometimes it acts like a particle and sometimes it acts like a wave. Well, this equation focuses on the wave-like nature of the electron, and instead of it being sort of a planet circling the sun of the proton, is basically a wave-like phenomena that we can probabilistically predict where it most likely will be, right? And also measuring the placement of the electron solidifies it to be in one place or another. But that's a different topic we can get into in a bit. But suffice it to say that this equation looks at the wave-like nature of the particle. So let's say the particle will have a distribution in its lowest energy state like this, where you measure the particle, you'd have a higher probability of finding it here and a lower probability of finding it here. And technically, you would still have some probability of finding it here, but it'll be very, very small, right? So when we look at electrons, we know that we have, well, how to say that we have the idea of orbits. And we know that if an electron has a certain energy, you'll find, excuse me, if an atom has a certain energy, you'll find electrons in certain orbits. So basically the placement of the electrons around an atom, that's one of the things that's ultimately determined by equations like this. We can probabilistically determine where this energy uh, amount is in this electron or in this atom, and we know that based upon that energy, it'll most probabilistically be there, and this is where we're heading at. For instance, the second one might look like this, where basically you can say we have uh, uh, oh, two sort of wavy points, three nodes technically. You can say this is a node and this is a node where it sort of crosses the lowest point. You can say this one has three nodes, you can say, and two wavy points, and the bottom one has one, but it's like a rough idea. And each time you go up the energy level of the electron, uh, with a higher amount of energy, you end up with more oscillatory behavior, and we can determine a proper probability from that. So basically, the state of the particle is generally thought of as this equation here. Is a bit more complicated than that, but um, generally this is thought of as a state, even though it's part of it. because it gives you the energy eigenstate that we can utilize to, like I was saying, construct and predict different placements of where the particle is going to be and the behavior that it can have. So what's going to happen is that the equation of the state will have to satisfy this equation. So what we can do is we can actually use this equation here to determine the energy of the particle. So let's say I'm dealing with a particle, um, and let's say that I'm going to choose the potential to be 0. So maybe I can have a particle, like some kind of well, like a tall well is a common uh, something you run into. So you can say that this is the well that we have a particle in, and we can say that outside the well, the potential is so big that the particle can't get through. So the potential out here is very, very big. And we can say the potential out here is very, very big. And then we can say the potential inside this well is 0. And we have our electron up in here. So the electron will be trapped in this area and will emit this wave-like behavior that fits inside this well. And basically we can use this equation to help clarify the energy and thus the states. So the way we can do that is we can take this equation and we can plug in those values. So that means since V is 0, we'll have negative h bar squared over 2m. Because the V component is 0. So now our state is going straight to the second derivative. So I can rewrite this as negative h bar squared over 2m equals EY. And to simplify this, I can multiply this over. So now we have a second order differential equation. So when you're dealing with quantum mechanics, you'll usually end up dealing with, at least in the early levels, I'm still in the beginning levels, second order differential equations. So basically our state is going to have to satisfy this equation. We're taking the second order derivative of that state, of that equation, outputs the state again, multiplied by some factor. So it's common to call this factor some variable. So I can say, for instance, uh, k squared equals 2me over h bar squared. So I can write this again and say this is my second order differential equation. And the state of my particle is going to satisfy this second order differential equation, right? And technically, like I say, I guess it's an ordinary differential equation because so I brought everything to the left side, doesn't have anything is multiplied by. I believe that'd be called a second order ordinary differential equation. And whatever equation that we have for the state has to satisfy this. So a common solutions will be either exponentials or trigonometry functions, because you can take a derivative of an exponential and it'll give you the exponential back, but it'll output what's in the numerator. So let's say if I make my state be psi equals e to the uh, kx. Well, the first derivative will give me k e to the kx, and the second derivative will give me k squared e to the kx. And thus it satisfies the equation because e to the kx is psi, so that's k squared psi. So This is not a specific one that'll solve the equation. It gets a bit more complicated, but this is the basic idea of it. That I have a psi, my function. If I take the second order derivative of that thing, it gives me my function back, multiplied by the uh, variable or a constant. Usually it's not a constant, but the variable in front of the, I guess you could say the value in front of the psi, and it outputs that. The same thing if I made my psi be sine kx, first derivative of that equals k cosine kx, and the second derivative equals negative k squared sine kx. If we look at this one, this one actually more closely matches our uh, given, because if you look at this, there's a negative in front of it, and this one not only does it start with a negative, it gives me my value squared, and it gives me my original psi, which means that gives me the entire kit and caboodle. Right? So that's an idea of how that works. What's going on, Gentleys? Gently says, hi, it's been a while, been a long time. I had no idea you knew anything about quantum mechanics. So I'm learning. So I'm training to be a physicist and a astronomer. So for both, you need quantum mechanics. Um, so like for instance, with astronomy, I plan on going to graduate school for astronomy, and the the whole thrust of astronomy, of course, has gotten a lot more advanced now, but still the foundation of it is we're looking into space and receiving the light from the objects that we're studying. Hey, what's going on, Lisa? Welcome. No problem. So we're studying these objects, and what we see is governed by quantum mechanics, to think about it, because, and I spoke about it a little bit last week, how if we have light coming from, let's say, a distant galaxy, we have a distant galaxy out there, and let's say we want to know how much matter is in between us and that galaxy. Well, the galaxy has a whole lot of stars, it emits a whole lot of light, but there's going to be atoms of hydrogen in between here. So some of that light is going to hit that hydrogen. It's going to excite it so that now it's excited. And then that hydrogen is going to emit that radiation again. It might go in a different direction. But we can know that there's a cloud of gas here. And, maybe it'll go ahead and hit a gas cloud. And let's say it has a different type of gas. Let's say this frequency here hits hydrogen. Let's say this one hits carbon and it emits a different way. Maybe it even emits to us. And we can know that there's something that has carbon there. Let's say the hydrogen just goes straight through the gas cloud. And all of this is happening because we have to understand that we have an electron. And we have an electron in this field around there. And whenever light hits it at a certain frequency, if it matches the frequency of the energy level of that electron, it'll absorb it. And so quantum mechanics is actually inherent in astronomy. Um, you probably saw one of my earlier videos. I talked about it a few times, how I took spectra of the sun. That's basically how that works. So basically we have the sun, and it's basically this fusion reactor that's just spitting out a bunch of light. But the thing is, the sun goes through this same process where it spits out, let's say we have our fusion in the core. This fusion spits out an enormous amount of energy, like a gamma ray or something. It hits something, is absorbed, and it is emitted out, and it hits again. So light takes like about 10,000 years, something like that, to actually reach us. So the light that we receive now has been traveling through the sun for like 10,000 years, being absorbed and re-emitted over and over again. And then when it actually emits out the sun has an atmosphere because even though it looks like a solid object in the sense that it has a definite border, you can more think of it like, to use the opposite example, like ice. If you ever look at ice and put it on a table on a counter, you see how it's frosting the air around it, right? Like it has a little halo of cold air around it. Is even some of the water vapor is coming from it as it evaporates. So yes, you can look at the ice cube and there is an ice cube there, and you can see the size and shape of the ice cube. But at the same time, that ice cube is steadily evaporating, and and part of the ice cube is actually extending in a gaseous state. So the ice cube that we see is technically not the extent of the ice cube; it extends a bit farther, right? If you get into the details about it. The way that happens with the sun is the same thing happens with the sun. It has its atmospheres extruding plasma and gases and things like that. It has a solar wind, so there's an atmosphere around it. It's so bright, usually we don't see it, but like for instance, in the solar eclipse, you can see the corona around the sun as an example. So when this light emits from the sun, guess what? It hits these particles here, is absorbed and emitted out, and at this point, this light has been emitted and bounced around so much, different frequencies are coming out. And we know that, for instance, hydrogen will absorb, let's say, this frequency. So now this frequency is missing in the light. So let's say the light from the sun would look like this if we were watching it. But now some blue has been absorbed out from the hydrogen, so that part is missing. And let's say this carbon is in there, absorbs some light, so that is missing. And if you look at my spectra that I took of the sun, you'll see that. You'll see some lines like this and you'll see a dip. You'll see some lines like this and you'll see a dip. And that is because of quantum processes. The atoms in the atmosphere of the sun absorbing those frequencies of light because it matches the energy of that electron. Then it spits it back out, But again, if it spits it out, it's going to spit it. It's not going to necessarily spit it back to us. But just like how in this example, the light that was absorbed here was spit out in a different direction. When we receive it, when we receive the light, we're missing that part in the middle. And this is what's happening here. It's the light that's absorbed. It was spit out again in a different direction. So when we receive the light, we're missing that light. We call that an absorption spectrum, and that's how we take spectra of the sun, and we can know what atoms are in it because we can see the things that are missing that have been absorbed and spit out in a different direction. Right? At least there's fusion needs a container. Hi, everyone. I'm late too. Still welcome, Catherine. Thank you. Most think is a ball of fire, and ironically, I mean, it's just that, of course, the dirt people, they believe they're dunking and they delude themselves into believing that misunderstanding things is somehow, it's amazing. I don't know. I am less interested than I used to be because I'm starting to, science is so interesting. And the more I learn, like I was very sincere when I said that they helped me appreciate it more because I'd be sitting in class and just seeing all the stuff that's going on and all the applications. Um, and it's just amazing that people could delude themselves to believe in that all this stuff is wrong, or even when we're using it now, like when we're using the electricity that we're using. So, but yes, quantum is definitely a part of astronomy. So, for both my astronomy degree and my physics degree, I would have to take at least introductory quantum mechanics. But for my physics degree, I have to take at least quantum too. So I got to do well in this quantum class, so I can take the next level of quantum, which will go into more detail. Instead of taking quantum 3, they do have quantum 3. I'm going to take a relativity course. I have to take some kind of higher level class, either relativity, quantum 3, or some other stuff that I wasn't interested in, like solid state physics and stuff like that. But I want some relativity in my life, so I took a class that had a survey where I took like a third of the class was relativity, but now I'm gonna take like a full relativity class. But I had to take some other classes before I got into that class. So, by the way, let me know if you have any questions about any of this. So, yeah, but that's that. So now let's look at how we can get the energy from this. So let's say, notice I pointed out, I picked some equations to solve this thing with, and I found that sign more closely related to my Schrodinger equation. And to review, uh, this is the Schrodinger equation. So this is the time-independent Schrodinger equation, to be specific. So this is the one that doesn't. There's a lot of processes before that gets to this point, right? But this is the one that does not deal with time. That's why there's only x there, and we could use the time-independent one to get uh, the energy eigenstate, so we can build up those other equations that we could use to predict things about a particle. So again, in this example, I'm choosing my v to be 0. And lo and behold, if I look at this, we can see how this works. I'll explore this with the sign equation really fast, right? So this is my well. I said I had a well. I have an electron or something up in the middle. The potential is 0 inside the well. We'll say that the potential is so big outside the well that the electron is never going to get this wall. Imagine like there's a wall that's keeping this electron in, so the electron is stuck, right? So now what I'm going to do is I'm going to determine some things that I can about the state of the electron just from the side that I picked. So what's going to have to happen is I'm going to have to meet boundary conditions in order to properly uh, understand and predict things about a particle. We have to take into account the conditions within which that particle exists. So if I was to label this 0, and let's say label this A, we know that this particle, whatever it's doing, is going to have 0 activity on the 0 part. It's going to have 0 activity on the A part, because that's where the infinite well starts, or the big well starts. So we know that this particle, so when I drew these waves up here, these waves are going to be inside. So the potential I saw there, that's the blue line, that still takes effect. And what I'll do is I'll copy this over on that well to see if it's more clear. So basically, the particle is going to have to fit inside this well. It's going to have a lot of energy states that can do it, but we know that the edges of the wave is going to have to fit inside of there, right? So when it gets to this end, the value is going to be 0. When it gets to that end, the value is going to be 0. And each of these different waves is going to be another energy level, and we'll get to that momentarily. But each of these energy levels is going to have to fit inside this world, or it's not going to exist. And Catherine says, can this happen in real life? Something preventing an electron from moving like that? Definitely. Yes, definitely. So right now I'm still in the beginning part, so we don't talk so much about applications to that degree. But my professor, he works at, like, his research is doing that. Like, he works at either CERN or, meaning like he works at UT, but I'm saying when he does research, he goes to CERN, or what's the other? I forget what the name of the other big collider is, but it's one of them, one of the big colliders. And that's what they do. Like, you can take a magnetic field, for instance, and so going to electromagnetism, we know that if we have a charge, when the charge is moving in the magnetic field, is going to have a force on that charge, right? So what they do is they take, this is one example, they take a electron and they spit it out, let's say. They spit this electron into an electric field, so excuse me, a magnetic field. So now you have a Q, negative, and it has a velocity. It's going in that direction. And let's say my magnetic field, and let me do it in the direction so I can draw it very easily. All right, so let's say my magnetic field is going into the page. So my magnetic field is going like this into the page. So what we can do is we can get a magnet or devise an electromagnet, or whatever the case is, And basically, we have a steady magnetic field going into the page there. So what's going to happen is, according to this rule, the velocity is going that way, the electric field is into the page. We have a negative charge. So what's going to happen is there's going to be a force on this electron that's going to move it to the right. So when this electron goes into this magnetic field, it's going to start going like this. And keep in mind that the field is everywhere. Is enough field so that wherever that particle is, it's still in that field. So the same force is going to be acting on that electron wherever it's at, right? So imagine we shoot the electron in, the force, according to this equation, I believe it's called Lenz's law, it's causing that electron to go like this. So now the electron is going in a circle. But this is what we do as well. We put an electric field here such that the negative is on this side and the positive is on this side. So what happens is when that electron goes through that electric field, it's boosted faster. So now it's boosted faster. It makes a bigger loop. It's still in a magnetic field, so it's going like this. And then it gets boosted faster, and it's going like this. So what they do is they pump a bunch of particles up in there, and this thing starts making it go faster and faster and faster, faster and faster and faster. And that's what we're looking at. We're looking at a collider right now. So then you put let's say you put something here. Let's say you have something here you want to explore. Now I'm getting more into theoretical. I don't think we really not necessarily got this far in class. But let's say you put something here you want to ram an electron into to find out what comes out. So eventually this thing goes fast enough and goes powerful enough that boom, it hits this thing at like enormous speed, like at some fraction of c, and then boom, these things explode and they discover the Higgs boson or whatever, right? So this is a practical application of containing that electron in a potential. In this case, the potential is the force, the magnetic force that's coming from an electric field. So it's definitely practical. But just, when we're first starting, we don't necessarily define what's keeping it contained. We just say, okay, something is keeping it contained, and let's figure out what's going to happen with it being contained like that. And Catherine gently says, wasn't there a Nobel Prize for confining an electron? That I don't know. Yeah, something doesn't come to mind. I know there was I don't know if they won a Nobel Prize, but I know it was a very important experiment where we discovered that the electron is wave-like because there's different particles of carbon, different elements of carbon or other nickel or whatever. There's different uh, uh, elements that make very structured lattice-like uh, uh, objects of itself. And I can't remember the guy's name. I don't think I ever really memorized it in the first place. But what he did was he experimented with things and found a certain element that matched the wavelength of an electron. And he was able to send electrons into it at a certain angle and then get wave-like phenomena from the electron. That's I believe the first experiment we really proved that an electron is wave-like. Basically, he made an electron do the same thing as a double slit experiment. I'm sure we heard of the double slit experiment. We send a wave in, and then it goes through the different parts, and it interferes with itself, and then we end up getting interference patterns on the back. Well, he did the same thing with an electron by sending electrons into the lattice structure of a crystalline a compound. Is basically some precisely evenly spaced distances between the neutrons, between the nucleuses, and we discovered that. No, the reason why nobody got, and my professor spoke specifically about that. He said that experimentalists normally don't get Nobel Prizes because, I mean, there's so many people. Like when they discovered the Higgs boson, it was like, I don't know, dozens, hundreds, all working on different parts. So there was nobody that can really say, like what Einstein, when he discovered relativity, it was Einstein. It was just him, right? Or when they discovered that um, dark energy, when they discovered that the universe is expanding, it was two different teams. And they have the two leads of the teams. I talked about that in my dark energy, dark matter talk. So usually it's theorists that wins it because, it's few people working on it. But the Higgs boson, it was like hundreds of people. They couldn't really figure out who to give the prize to. And Catherine says, is it a magnetic barrier contained within a physical pipe? What's the loop at CERN made of, and what's it called? That I don't know the details of. Like, this is a general one. The CERN may not be made exactly like that, but I just know from one of my homework problems from my electrodynamics class that there are devices like this, and that's what they use it for, to accelerate electrons. So I imagine one at CERN to be similar to like this, but the principle is pretty much the same. But it's probably just a very much more advanced something like this, where they have to accelerate a particle, they keep it trapped in some kind of field, most likely a magnetic field, and just keep accelerating it until these things crash together. So it's pretty cool. So, but these are the kind of things that, like the people I debated, for instance, they pretend like they understand electrodynamics and stuff like that, but they have no clue. They have no inventions that they've made that, you know, but we get electricity from people who understand electrodynamics and electrostatics and colliders and things like that. So these are the people who understand what's going on. So, but I do, there's no bits and pieces of it, but I imagine I don't plan on taking electrodynamics too. But if I did, we'll probably cover more of that stuff there. Now, so we have this well, and what I'm going to do is I'm going to figure out my boundaries with a sine function. So if I have a sine function, I know that sine of 0 is 0. So that's a given. Now all I have to do is make sine of A also equals 0. And from earlier, using what I had earlier, I believe it was sine kx. So sine kx equals 0. So that means that kx has to equal n pi, right? Because any integer times pi is going to make it equal 0. So I can say that uh, k equals, hold on, I need to put in my a, ka equals 0. And let me put this here for clarity. We have the 0, we have the ka, k equals n pi. So k equals n pi over a, right? So now I have my boundary conditions confirmed. So I can say my psi was sine of kx. So now I know what k is, so I can say my psi is sine of n pi x over a, all right? And so now I have my psi that I can plug into my equation. Again, this is a simplified version, but this is how you do it when you start off learning it. And another thing I could do is to get the energy. Like I know that had that where here. So I know that a squared is this. I got that earlier from Schrodinger's equation. And now I have another k in terms of my boundary conditions. So I can say k squared equals n squared pi squared over a squared. So I can equate these things and say 2me over h bar squared equals n squared pi squared over a squared. And I can solve for e, and I get n squared pi squared h bar squared over 2m a squared. And what this is the energy of an electron or a particle inside a well. So if you have a well like the one that I had earlier, this gives you the energy of each of the levels. So in other words, the lowest level, E1, would have the energy pi squared h bar squared over 2m, the mass of whatever the particle is, and the width of the well square. So this will give you the energy of that first wave that's inside the well, depending on the dimensions of the well. You know, to look like that. And this will be 0 to a. So let's say if a is 5 meters, then you're plugging 5 meters squared If it's an electron, you'll plug in the mass of the electron, and so on and so forth. And that will give you the energy of that particle in the first state. So that's just a brief idea of how we get the energy of a particle in that well, how we get the psi to eventually be able to predict things about the particle, where it's going to most likely be. And ultimately, this stuff ends up leading to how we know the general positioning of electrons in an atom. How do we determine what those orbits are? Like, for instance, I talked about the uh, uh, like hydrogen emitting at a certain wavelength. There's specific frequencies of all that stuff. Like there's the Balmer line and the that's the one that comes to mind. Uh, the out That's the first one. It's the main one of the main ones. Each of these lines has a certain frequency. So basically, let's say if the electron drops down from the second orbit to the first orbit, or the third orbit to the first orbit, it'll give you a certain energy. And each of those are very precisely known, and that's how we can know where these orbits are and everything. And Catherine says, why do we use this? Why do you use a sine function for the barrier? I need this, certainly. So the reason why is because I have to meet this boundary condition. So what I decided was, I said, I'm going to put this particle in a well such that particle can't get out. The particle is going to be stuck. So in order for the particle to exist, the wave has to exist fully in this well. So this is similar to literally the waves class. Like if you ever played with like a water pipe, and if you have a tall pipe and you start filling it up with water, unless you have a tuning fork, and we have to actually do this for our waves lab. If you have a tuning fork over this thing and you hit the tuning fork, so now it's emitting waves, you only going to hear it when the water reaches a level that matches the exact length of a wavelength. So here you will hear a very loud tone because it perfectly matches. Here, when it's halfway, you won't hear nothing. Here you'll hear something because it's a full wavelength. Here in the middle, you won't hear nothing. And that's where it really works with waves. So the way it works is this full wave has to fit inside this thing. And if it doesn't fit the full wave, you won't hear anything, right? So the same thing has to happen to the wave nature of a physical particle. When you're dealing with a particle's wave nature, the particle is only going to exist if it fully exists within that space, and it fully exists in that space when the wave can cover the full width of that space. And when the wave covers the full width of that space, it has to be zero on the left side because I've defined this potential that's not going to let it out on the left side. It has to be zero on the right side. Now, if I did cosine starts like this. Cosine starts high and then goes back up, but it has to be zero on this side. So that's how I know it can't be cosine, because cosine starts high. Only sine starts low. Sine starts at zero off top. So I know I'm going to start with sine because this is already satisfied with sine. I know my left side is going to be zero automatically. And then all I have to do is figure out what value of sine is going to make it zero at A. That's why I went through this step. As long as my K is n pi over A, then my sine is going to always equal zero at this edge. And now my particle is going to fit inside this well, so it can really exist. Just like how the sound is going to only exist when it fully fits inside that well. You're welcome, Catherine. So that's how that works. And sine is one of the most simple ones. Some of them works better with exponentials. It'd be something like e to the kx, or even e to the negative I kx. So ironically, a lot of this stuff, like if you look at the uh, imaginary exponential, all that is a bunch of sines and cosines. But it turns out that a lot of this stuff is easier to work with if you work in imaginary numbers and then convert it back to sine or cosine whenever you need it. So a lot of the stuff we're doing now, we end up using exponentials, unless it's for a very specific reason. But this is like one of the first types of problems that you deal with a well that the particle has to fit. And in this case, this will be A, this will be zero. So you end up using a sine wave. Certainly. So basically it works like this. The Schrodinger equation is -8, and this is the time independent one, over 2m, second derivative, psi, plus the potential energy, psi, is going to equal the energy of the system, psi. And what we normally do is we factor the psi out. So we have h bar squared over 2m, second derivative, plus Vx psi, and that still equals E psi. And this part right here is normally called the Hamiltonian, as an operator that gives me the energy. And then what I can do is I can go ahead and simplify, and let's say this time I don't make V 0. Let's say V is just what it is, right? So what ends up happening is I would distribute this and say h bar squared over 2m, second derivative. So as a matter of fact, I'll just write it like that, plus Vx psi equals E psi. And I'll do the same thing. I will get the psi by itself. Now I'm going to have E psi minus Vx psi. And then I would go ahead and factor that to figure out what's my beginning component. So now I have E minus Vx in the front this time. So a little bit more complicated. Psi. And I could do the same thing and multiply that over. So I have psi double dot. It's going to be 2m E minus Vx over h bar squared psi. Now this is going to be my k squared. So k squared now equals 2m E minus Vx over h bar squared. And this might be a situation where you have a potential where, let's say, potential is, so this is my x-axis and y-axis, let's say. And I'll say my potential is, let's say, like this. So now it's not very infinite. Let's say it's like that. So that, let's say here it's 0. But let's say here it's just negative V naught. But there is a V there. And let's say here is 0. So before I made my well, so inside the well was 0. So therefore I was able to just do away with it. And out of here was basically infinity. I had to worry about that because it wasn't going to get out. But let's say here I do actually have a potential. It's a negative V naught and 0 elsewhere. So now I have to keep this. So technically this, if I call that V naught, negative V naught, this will be minus negative V naught, so plus V naught. And that'll be my k squared now. So now I would have to do similar to what I did before, but it ends up being a bit more complicated because now my k squared is pretty, it has the energy and it has the V naught. My equation is going to be a little bit different because now I have an equation here for where potential is 0, and the equation here. So basically here I might have psi of e to the negative kx, or actually positive x is going to the right. Here I might have sine and cosine. And here I might have, let's say, psi equals e to the negative kx, for instance. And then I would have to do a more complicated process to figure out what's going on. And Catherine says, sorry, the sign one for the electron barrier. Oh, no problem. So all we do is we figure out, I picked sine because I needed my left side to be 0. And now I need to find out what value of sine on the right side is going to make that 0. So basically, sine of 0 is 0. So that takes care of itself. And I had picked my sine to be sine of kx. So literally, I just started going through some things. Like I started with my exponential, and I just went through some things to see what fit better. Sine happened to fit better, so I'll work with sine and see what it does. And all I have to do is, I said my equation was psi equals sine of kx, but I need whatever this value is to give me 0. And I know that if I take sine of pi, I get 0. If I get sine of 2 pi, I get 0. If I take sine of 0, I get 0. So basically, this is sine of n pi is going to give me 0. So that means my Ka needs to equal n pi in order for it to be 0. Whatever my Ka is, it needs to equal n pi so I can get a 0 on the edge here. So then I just solve for K, and now I know my K has to be n pi over A. If my K and my psi here is n pi over A, then I'll always be able to get 0 on the right side. So now my boundary conditions are met. I have 0 on the left side because I'm using sine, and I have 0 on the right side because that's what I picked. And all I have to do is plug this K into my previous equation, and then I get what energy I'm going to have for that particle. So I know the first level is going to have this. The next level is going to have E2. I'll put in 2 for N. And as you can see, the energy is discrete. And this plays into the fact that, or acknowledges the fact that that's why when we shoot energy at an electron, for instance, if I shoot energy at a hydrogen atom, I can't just shoot any type of energy at it and it shoots light back. I got to shoot energy at a certain frequency. So if I shoot energy at E1, the electrons at E1 will capture that and send it back. Then if I send something at E2, the E2 electrons will send something back. But if somehow I turned up my energy a little bit more, so I'm sending technically what will be E to the 1/2, nothing is going to come back. That's called the photoelectric effect. That's one of the ways that we know as well that this stuff works, because nature itself works in this way. Only when you hit an electron with a specific n number of energy, E1, E2, E3, only then will it absorb that energy and excite. And when electrons emit energy, they only emit energy at some definite E1, E2, or whatever, because that's the energy that it has, and it excites and throws that out. So it all adds up. So Schrodinger's the man. So, and of course, we developed it a lot since Schrodinger, but he's the one that started it. So awesome. Hope y'all enjoyed the basic intro into some quantum. So we pretty much talked about Schrodinger's equation, so how we can use it to get the energy states of a particle in the well, how we can get psi, and some interesting stuff that you would learn in the first year quantum mechanics class. And I'll be back next week. Next week, I'll probably do some electrodynamics. So the reason why I'm doing quantum now is because I have a quantum test on Monday. So hopefully I'll do well. I'm still in a position where I could do really well in the class. So when I have to make sure I do really well on my final. And then I have an electrodynamics class the following week. So be prepared for some electrodynamics next week. And I'll see what kind of electrodynamic stuff I'll talk about. Think about the Ant-Man suit, by the way. Since I've been in this class, is it possible? What happens when he shrinks? Like, does the atoms actually shrink, or does he end up with less mass somehow? I don't know. It's an interesting thought. Uh, uh, Pretty sure something like that could be possible because there's so much space. Like even in an atom, everything is mostly space. So there's definitely enough room for somebody to shrink stuff down. I remember one of my favorite movies as a kid was that Honey, I Shrunk the Kids movie. I don't know if y'all remember that, Honey, I Shrunk the Kids. That was very fun. So I don't know if, pretty sure that came after Ant-Man. Um, but awesome. I'll look for y'all next week. We look forward to some electrodynamics next week. Y'all have a good evening. Thank y'all for showing up. Thank y'all for chatting. Always good interacting with y'all. See y'all next time.